Day 55, daily LeetCode. Day 55, daily LeetCode. We're back once again. This is day 55. We have some problems lined up for knocking out. We've got minimum stack, right? Which also reminds me, we need to start doing some heap problems, but it's just another item to add to the backlog. I'm actually thinking now that we probably want to read a book on, or maybe some articles on DFS or something. Because we were doing some work, we were doing some problems on the Explorer card, right, on the DFS, but I'm thinking there's not enough surrounding context, so maybe we can pick up the ADM, the Algorithm Design Manual, and start reading up a storm, maybe start, ingesting some informations. That being said, we have min stack lined up, actually. We have min stack lined up and number of islands. So we're going to do those two, right? And then we're back. We have to show up once again, right? We're still in prison, right? Longest nice substring. This problem, right? We did a n-cubed solution. The time complexity was horrendous, however. It was unacceptable on many accounts, in many ways. Just not acceptable, right? So we got to do better. That being said, I think today is the last day we'll spend on this one, because I think, if I was asked to optimize this, I'm not really certain how I would do it, but I'm sure we'll know after the solution. But either way, I got to explore a lot of different solutions for this. Even last time we were talking about a version that would use binary trees. It would use a tree, but this version, even this version that I came up with was pretty cool. So we might just implement it for the sake of implementing it, and then see if we can glean some insights there. That being said, I think on the last video, I just sat in silence for like 10 minutes and thought, and I think that's where the growth happens, right? So I'm not even really solving this problem except for the brute force solution earlier, but yeah, it's just interesting. Yeah, it's just interesting. It is just interesting. Yeah, it's just interesting. Something's interesting about it. That being said, yeah, we have some other things as well. So we're gonna do these two problems, right, and then jump into longest nice substring for our final chance. We also got a dope tip from our boy T Wong, legendary HCC member, as well as Just That Guy, also another legendary HCC member. And then we have one of the most legendary HCC members of all time, the Copy Ninja, the Control C Ninja, the Control C Espionage Master. But my man Thomas mentions that a brute force sliding window based on the number of unique characters. If you know, you know. Maybe do it with DNC. And I'm also realizing on the Explorer card, we need to do a divide and conquer Explorer card very, very, very badly. Like, it's actually crazy how under, right? When you're getting better, the best place to get better is your weakest spot, right? And it's crazy how on the divide and conquer, when it's a potential solution, we just can't implement it. So that's pretty bad, right? So I'd like to be able to do something about that, hopefully. That being said, yeah, we're gonna try and take this advice into account. Our boy would never lead us in the wrong direction. So I believe, right? Additionally, been doing some problems on Brilliant, and I think this also may be another way to expand the brain follicles, the brain mounds, the brain sauce, the brain wrinkles, right? It's just an easy way to, I think, like they mentioned on the website, build intuition. So I think it'd be a cool way to just kind of casually learn stuff on the side. But I'm thinking of doing Brilliant on the side, and then just as a low effort, it's like a low effort way to stay involved, get exposed to some things. I might do that and then pick up the ADM. But I'm also wanting to increase my system design skills. So competing priorities as always. Maybe there's a way we can parcel this out, right? I can't negotiate on the hour and 30 of LeetCode. It is just too strong, right? But it would be awesome if I could supplement it with something else, like the ADM. And then I read Alex Zhu's system design interview book, which is pretty awesome, but I need some actual practice designing systems just for future projects. So I'd like to do that. And then from there, I think we'd be able to develop slowly. Hopefully it will develop slowly in the right direction. So longest nice substring. Yeah, so we'll do those two problems, longest nice substring. Maybe we'll pick up the ADM, and maybe we'll start adding maybe like 30 minutes. Maybe this probably be unrecorded, just 30 minutes daily of system design. Maybe after a month, that would be how many hours, right? Every day is half an hour, right? So I'm guessing at the end of the month, it would be like 15 hours, right? Because it would do every day half an hour, 30 days, half an hour each, should give 15 hours, which is actually kind of crazy. No, there's no way. Oh, no, yeah, that makes sense. That makes sense. Right. That being said, we're back once again. We've recovered, right? I think I said earlier as well, a few days ago, we did like 8 hours or 7 hours, something like that. And then what was required later on, I think it was on Friday, August 5th, we did like 7 hours or something, right? Then we needed to do 2 recovery days, basically at 30 minutes. Wait a sec. Oh, no, you're right, I forgot. Yeah, this one says August 8th. Another thing, when I upload these videos, it takes like the video's an hour and a half, it takes like an hour and a half to upload, and then YouTube has to process it, and it can't go live until it's processed. So it takes another like, literally like 2.5 hours. So when I upload a video, like if I'm starting at 7:30 right now, if I upload the video right now, you probably won't see it until like 1 a.m., which is kind of ridiculous. I mean, it's not ridiculous, but also my upload speed is trash, but the processing speed is also tough as well. That being said, right, these date markers don't line up perfectly, but I promise you for every day there has been a video. But if I miss a video, I know the subscribers got me. Their grind never stops, so it must continue as well. So we have, we have these 2 problems to do, and then we'll do longest nice substring, right? And then afterwards, I really think today is the day. Actually, I don't believe today is not the day. I don't think we're gonna be able to get this to linear time, but something is fun about trying to get it there, right? Man needs puzzle to solve, right? Even the cavemen needed puzzles to solve. The puzzle was survival, right? And now the puzzle is LeetCode problems. That being said, I think yesterday, Thomas, just that guy, and Copy Ninja, we hopped off a call with Joe Byron, right? We finished up, right? Last week we settled on 33% of the US's networking infrastructure for the HCC, and I just had to call. I had to FaceTime in the middle of the night. I was just like, yeah, we need more. So we actually got slightly knocked up to about 40% of the US's networking infrastructure. So that way, when you go to the HCC Discord, I mean, you can actually load up the messages, because before we were having a real problem with that. So yeah, after that, I don't know if we're going to be able to, we're going to be able to get any more resources from the government. So probably going to have to start talking with, we're probably going to start talking with the Discord, the guys at Discord again. Hopefully take some more, hopefully reroute some resources so that more people can join the HCC. But don't forget to join. The Hyperbolic Coding Chamber is a new Discord created to help you do anything. I mean, yeah, so the Hyperbolic Coding Chamber, people are rapidly improving their programming skills at a rate never before seen by man and women. So you're going to want to join. There's a lot of secret tips, a lot of secret cheat codes. So yeah, even for artists, I mean, there's this particular number of like keystrokes in a particular order, right? If you're an artist or a graphic designer, if you type them in the correct order, you actually spawn an instance of DALL-E 2, right? And then you can sneak in a prompt. It'll automatically generate the prompt. And then the final step is profit. So you're going to want to get that cheat code. It works on any modern operating system. We have a team injecting this code into every binary of every package of every operating system. So it's just a necessary evil. That being said, That being said, right, we have an hour and 30 minutes on the clock. I've just consumed some nutrients, right? So now we must feed our brain wrinkles more information. So let's jump into it. We have min stack number of items, longest nice substring. Let's do it. So given an M by N 2D binary grid, given an M by N 2D binary grid, which represents a map of ones, land, and zeros, water, return the number of islands. An island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. Interesting. You may assume all four edges of the grid are all surrounded by water. So here we have the grid, right? And they're saying the island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically, right? And we're returning the number of islands, which does match up right here, which would be a number, right? And so we have 1, 1, 1, 1, 1, 1, 1, 1, 1, and they're saying that islands are formed by connecting adjacent lands horizontally or vertically, right? And anything outside of the grid is water. So if that's the case, then I think what we're actually going to have, right, is one island, and that's what our output is here, because all of these ones are connected horizontally or vertically to one another, and so they all come out to one island. We have this one we have 1, 1, 1, 1, 1, 1, 1, 1, right? This group of ones, right, is not connected horizontally or vertically to this group. This group is not horizontally or vertically connected to this group. So we have 3 total islands, right? We have M is equal to grid length, right? And N is equal to grid sub I. So we know we have a uniform rectangle, right? And we know that M, right, will at minimum equal 1, and that N will be greater than it or equal to it. So we know we'll have at minimum 1 row and 1 column. Also, the input in the matrix is verified to be 0 or 1. Interesting. So I think we usually have a method of solving this, right, which involves doing an M by N iteration through the grid, right? So we could view this, right, as an M by N iteration through the grid. We have, right, iterate through the matrix, right? Whenever we see a 1, we'll do a depth first search based on the rules specified here, right? So as to clean the nearby islands. For example, if we bring our input over here, right, we can see is we can do this, right? We'll have 1, 1, 1, 1, 1, 1, 1, right? What we want to do is actually, right, so we'll find a 1, right? And then from here, we'll start a depth first search, right? But this depth first search will only go up, down, left, and right to only find the connecting islands, right? So we want to output 1 here. So if we find a 1, we'll increment islands, right? So we found a 1 because this is the first element in the matrix, increment islands by 1. Then we're going to call clear nearby islands, right? So it's going to change this to a 0, right? And it's going to go here, right, here, and here, and here. And it's going to come back here, 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 and here. And notice it's only going to visit nodes which are connected horizontally or vertically, right, based on our rules, right? And then we can continue iterating through, looking for the next one. What we'll see is there's no longer any ones to find, so we can return 1. What we can do is iterate through matrix, right? If find 1, DFS, right? DFS clean near by islands, right? And so what is the runtime of this algorithm, right? if we have the worst case, right, is that we have a bunch of ones which are not close enough to be depth first searched, right, but started depth first search anyway. So something like a bunch of zeros here, right? This will start a depth first search. We'd clear nearby island, clear nearby island. Maybe it's something like this actually, right? Where it's like tiled, right? Where we barely get to reuse our work. And let me make this slightly bigger, right? If that's the case, right, then our number of, at the minimum, we have to do m by n iterations, right, to find all the ones. So we're going to do m by n. An m by n matrix, right, now what's the worst that we can do? All we can do is visit our nearby islands. The worst case is that the whole matrix is ones. In that case, we'll do an m by n. In that case, we'll do an m by n depth first search, right? So I think this algorithm actually runs an m by n squared time. Because the worst case for our algorithm actually, no, I think it might be m by n time. Because imagine this, if we visit our whole matrix, right? If we visit the whole matrix, right, it's all ones, we actually won't revisit what we've already revisited. So we'll turn all ones to zeros, and then we just do the remaining. So in this sense, wouldn't it just be, in the worst case, right, m by n plus m by n, which would just be basically be 2m by n, right? But I know we've submitted this before, and it's not very fast. Oh, actually, this, okay, it's actually relatively fast. I wonder how fast it is. So like 50% memory-wise. Okay, so it's not the worst thing in the world, actually. I wonder if there's a fast, oh, we can't get sidetracked. We're not really looking for a faster way, but I just actually had another thought. I think it's just 2m by n, but it's still technically 2m by n. Could we do it in m by n time? I'm wondering if there's a way to do this, and I think there is, with union find. Because another way, we can imagine a subset of islands, right? If we imagine this island, or this grid here, we can imagine this subset of islands, right, these three islands, right, as what root nodes, what is their parent root node, right? What would be their parent root node, right? And their root node would just be whatever one, right, starts it, right? So we go 1, right, find the neighboring ones, add them. But this is no better than finding neighboring ones would require depth first search, which would be no better than our algorithm here. We'd just be making it more complicated. So we need a way to iterate through the matrix and pretty much add an edge to something. So could we visualize this matrix as a graph, right, where we only care about groups of ones? We only care about groups of one. For example, if we find this 1 here, what if we check horizontally and vertically, right? We check below us, above us, right? But that would be more breadth first searchy. If we did more breadth first searchy, we might as well turn them to 0. There's not actually an efficiency gain there. It seems the problem lies when we're iterating through, there's actually no way to tell what parent a node should be without doing some sort of DFS or BFS style work. Yeah, this one's tough. I think you can use union find in some way. I'm just curious if it would actually give us better time, but let's try our regular solution. But it's good we got to explore a little bit on this problem. All right, so we want to iterate through the matrix. To do that, we'll have two variables, row and column. We'll have grid dot length, right, row plus plus. We're going to duplicate this because we're going to want a column as well, right? But the column is actually going to depend on the row, right, for this particular, or the length of this particular array in the matrix. That being the case, since we guarantee that our matrix is a rectangle, we're relatively safe here. I wonder why our window is doing this. Usually we doesn't do this. Maybe it's too big. Right, so I have if grid sub row sub call equals 1, right? And like we said, now we're going to want to clean the nearby neighbors, but as well we're going to want to have this islands variable which we set to 1, right? And then we're going to return islands. If we find a 1, right, we can guarantee this is an island, right? Then we're going to clear all the nearby islands so we don't have any repeating calls. So say clear nearby islands, right? To do that, we're most definitely going to have to pass in the grid, right, our current row and column. And do we need any other information? I think we might be okay for now, right? Then we want to clear the nearby islands, so we can create this clear nearby islands. This is going to be a depth first search, which takes our matrix of 1s and 0s. Right, so we're going to want to update this 1, right, to equal a string, right? And we're going to have a row, which is going to be a number. We'll just change this to R so it's easier to type. I have C, which will be a number. We're not going to return anything. And the first thing we're going to want to do, right, we're going to want to check, right, that our current cell is valid. When we start our DFS, we're going to know for certain that our cell is valid, but our future DFS that are spawned by this, we're not going to know if they're actually valid. So we know that we find this 1 here, it's valid, right? So it seems strange to validate it. But we're also going to have to check above us, left, right, below us, and right. And so we're going to also need, right, well, I guess to start, let's do that. So say grid, right? So in TypeScript gives us a cool feature called safe navigation, so we can use that, right, to check if this cell value is a valid cell value. And if it is, right, the first thing we want to do is set grid sub R sub C equal to 0, right? Because what 0 does, it turns it to water, and our double for loop only starts the nearby search, right, when it is equal to 1. So if we change it to 0, that means it's all the islands connected to this island, right, won't create a scenario where we increment islands, right, unintentionally. So we're going to want to do a DFS here, right? And the other thing we're also going to want to make certain, right, is that we want it to exist, right, but we also want it to equal 1, right? If it exists and it equals 1, then we're in business. All right, so then we're going to need a couple of clear nearby islands. I'm going to pass in grid, right? We're going to want to check above us. To do that, right, imagine if we are in this line right here. To check above us at this one, check above us, right, this is going to be row 1. Check above us, we're actually going to have to do R minus 1, and C can actually stay the same, right? And then we're going to do R plus 1 to go below us, right? And then we're actually going to have these two change, and we're going to do add 1 to each of these. To go to the right, we're going to add 1 to the column, and to go behind us, we're going to subtract 1 from the column. And so this makes sense from a high level. Let's see if it makes sense on run. Oh, so this actually seems pretty fast. I mean, it says 81 and 90%. Earlier, it was not that good, right? So I'm thinking the time complexity of this would be m by n in the worst case. In worst case, the entire matrix is filled with ones. So on the first one, we'll visit the entire matrix, but then we still visit the rest of the matrix. I wonder if there's a union find method. All right, so it's O of m, right? And the space is also O of m. So O of m by n. Ah, you can use union find. I knew you could use union find. I wonder what the time complexity is. It's still m by n. That's what I was thinking. I knew. I'm still curious. I kind of want to read it to see how they did it. But I knew we could do it somehow if we visualize it as a graph. But I was wondering how you would actually create the edges. Maybe you would just automatically say that a node is connected to the 4 nodes around it. It's undirected, right? So I guess you could just do that. Right, but then what would actually be your indice? What would actually be your, right, how would you make, because the union find, there's a root array where the vertex is labeled by the element's base index. So how would you actually map that to how would you actually map that to a matrix here? I kind of want to read how they did it, but I don't know if this is cheating. It could be something cool we try to do in the future. This would be kind of cool to do in the future, try to figure out a union find solution. Let's save it and we'll make a mental note. We'll try a union find in the future. I don't want to read it because I want to try and figure it out. Seems like a cool thing to try and figure out. But that works for so far. Let's do min stack. So design a stack that supports push, pop, top, and retrieving the minimum element in constant time. Implement the min stack class. Min stack initializes the stack object, right? Void push int val pushes the element val onto the stack. Void pop removes the element on top of the stack. Top gets the top element of the stack. Get min retrieves the minimum element in the stack. So design a stack that supports push, pop, top, and retrieving the minimum element in constant time. So I think push, pop, and top you get for free in constant time, but actually retrieving the minimum element get min is actually the hard part of this problem, right? We need constant time for every function, every element in every method in the class, right? So they create a new min stack, they push -2, they push 0, they push -3. Get min returns -3. Now we pop the element on top of the stack, which should be -3. We check the top, it's 0, and the new min is now -2. How did they accomplish this? Right, I think what they're getting at here, right, is that what you could do is use a either an array of tuples or a parallel array, and the goal will be as the first array grows, right, the first array will always have the smallest. The first array will actually keep the values in the stack, right? The second array will keep the minimum value at the time that that element was added into the stack. And so what we can do, right, since the stack is last in, first out, we can take elements off the top of the stack and not ruin the min at the bottom. Whereas if we did this with the queue, it would essentially break the algorithm. So right, we want, right, 2 parallel arrays. Now to do that, right, we'll have R, right, which could be the array to start, right? It'll just be an array of numbers. You could duplicate this and create an array called min, right? This would be a minimum array, right? This would be our parallel array. And our constructor, it doesn't say our constructor needs to do anything, so you can actually delete that. Right, when we push a value onto the array, onto the stack, right, what do we want to do? right? Well, there are two cases, right? For example, if we push an element onto the stack, right, and the stack is empty, well, what's the minimum element so far, right? It would be the element that we're adding, right? So we want to do, right, if r.length equals 0, right, then what we want to do is r.push val, right, in the smallest, oops, we're going to want to fix this to this.r, and the smallest value so far is actually going to be the value we just added, right? Otherwise, everything changes, right? Well, this.r.push actually stays the same, right? But what changes with min, right, is the smallest value is actually going to be the smallest value, right, of, and to make this much simpler, we can just do this like this, right? If the array length is empty, right, then we'll push the value onto min. Otherwise, right, we're either going to want to push the math.min of value, right, or the last element, right, in min, right, either the minimum of either the current value or the last element, right, that was the current minimum, right? So this.min.length, right? And basically what this does, right, it basically takes the min of the previous min, right, and this new value, right? Because we see here at -2, they can push a new value on top, -3, which is the new smallest, right? And so min is actually either going to be, right, -2 or -3. In this case, it's actually going to be -3. Right now, when we pop, right, can we guarantee that when we pop, stack won't be empty, right? Always be called on non-empty stacks. So we can basically just do this.r.pop, right? We can duplicate this for min, and we'll just pop the element off there. Now to get the top, we're going to get the top element on the stack, right? And they're saying top also and min as well will never be called on empty stacks. It's saying it'll always be called on non-empty stacks. So we can just return this.r sub this.r.length -1. So we're getting a top element on top of the array. Right now to get the minimum, we kind of just have to do what we did for top, except we want to do it, right, on the min array. Right, so this makes sense. Let's try. So it works for the first case. So this makes sense. So all these methods should be constant time, right? Pop, right? Anytime you index into an array, right, it's going to be constant time. In most languages, right? So min, top, and pop are all constant time. Moving an element at the end of your array is constant time. Moving an element at the front actually takes linear time if you're using like a dynamic array. Pushing here is going to take constant time as well. So I think we should be safe. Right, actually I'm thinking after longest nicest substring, we're definitely going to have to go back to review. I'm realizing we haven't done review problems in a long time. So yeah, this is a tough one. Yeah, like we said, we got to finish the review, so we'll keep doing that. But a string S is nice if for every letter of the alphabet that S contains, it appears both in uppercase and lowercase. For example, AB, right, lowercase, and then ABB is nice because A and A appear and B appear, right? And you can have multiple as long as those first two exist. However, lowercase b, capital A is not, because we're missing a capital B. Given a string S, return the longest substring of S that is nice. If there are multiple, return the substring of the earliest occurrence. If there are none, return an empty string. So we went through a lot of approaches so far, right? And what we're seeing now, right, what we're working on, we're seeing that we can model it as a tree as well, right? Where for each instance in the tree, we'll either remove a character from both the left and the right hand side, right? And then if we find a nice string, we'll return it. but the time complexity was unknown, right? We were following this tree down here. We know that A, capital A, lowercase a is a nice string, right? If we know that, then we could do one of those things, right, where we continue to fuse upwards, right? But we know ZAA isn't a nice string. Saying you could also do bit manipulation, divide and conquer, sliding window. We did sliding window, but the time complexity was awful. Hash table. Maybe we could try, like Thomas said, an optimized sliding window, right? It's based on all unique characters. Now, what could we do with all the unique characters? Move for sliding window on the number of unique characters. 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 So if we have Yaza A, right? We have, I guess we can do lower case insensitive and case sensitive. Right? Case insensitive, we have A, Z, Y. Right? Now if we do case sensitive, we have AA, Z, and YY. I was thinking that maybe we could make trying to make this unique character thing work, but I can't think of a way that makes sense. Z is our only unique character, right? But I think earlier we had a concept of a pairless character. A pairless character is technically a unique character. We do brute force on pairless characters. For example, if we added a B here, this would also be a pairless character, right? The new longest nicest string becomes A, lowercase a, capital A. Now, if we did that, right, we would have two pairs. We'd have YA, right, which would be a potential, like if we split on pairless characters, we'd have AA, right, and then AY. Now, if we did our algorithm here, our tree-based one, we could find if a string is nice, right, then we'd be on to, maybe we'd be onto something. But for a string of size 2, it does, actually, it's pretty quickly able to tell if it's nice or not with 2. In this version we tried 3 days ago, this one was very, very slow. Pretty much generated all strings. Not all strings, but all strings where order matters. Right, we had a linear time is nice algorithm. I think we can do an optimized, actually, if I copy this, I think we can do an optimized brute force, right? Our isNice function takes linear time, right, and linear space. We're generating all these strings here, right? Maybe we don't have to. Right, we're also doing a sort here, which bounds us, right? What if we just say let longest, we'll just let nice equal to an empty string, right? At the end, we'll change this to be longest nice, right? And we'll return longest nice, right? Now, if there's no longest nice substring, then we return an empty string, right? But at the same time, we're going to want to do something different than a for loop. I'm going to do a while loop. So we can let I equal to 0, and say while I is less than s dot length, right, and right, I right? Let's say we have a string of length 6, right? We know that our longest, nicest substring is of size 3, right? If our longest, wait a second, there's multiple, then we'd like to return the first. Then, and that's the case, we'll only check one if it's greater than, right? So we'll say that longest nice equals, right? So we have 6 right now in our while loop. If I, right, minus, or I, let's say I is less than s dot length, and I plus longest nice dot length is less than s dot length as well, then we'd like to continue, right? So one way to say is we have a longest nice substring of 3, right? A, right? We don't want to check the remaining 3, right? Because we'd be at index 0, 1. So maybe we have something to write at. Let's say we have something like this. Our longest nice substring is capital, is this subset right here in the beginning, right? Now if we get to index 0, 1, 2, right? At this point, we know our longest nice substring is 3, all right? It's length of 3. Now we're at 0, 1, 2, 3. If we do 3 plus 3, right, and it's not less than 6, right? Oh, it's not, and I is less than or equal, right, then there's no point, right, of going further, because we're not going to find a string that can be longer, right, because we don't have any more string left, right? That being the case, we'll add an I plus equals 1 down here, right? But now you want to do something slightly different, right? We're going to generate all strings, right? Since we're generating not all strings, but all strings or order doesn't matter. This is still going to look the same. We're going to push a string. We're going to have a similar thing like we did before, like we have up here though, right? We only want to run this. So another way to say this, right, is if, actually I think we're safe here. We don't have to duplicate this here. For example, basically we're going to try to build all versions of this string, not all versions, but yeah, I think all versions, right? YAZA, right? Then we're going to do AZAAY, and then ZAAY, and then AZ. But on each iteration we'll check, so we pretty much build every version of the string. Now if our longest version of the string is going to be lowercase a, capital A, lowercase a, right, then there'll be no point in checking the remainder, right? But this only helps us when our longest substring is front loaded, right? What about when it's not front loaded? What about when it's not front loaded? So say if string dot length is greater than longest nice dot length, right, then we'll be interested in running this linear time algorithm. Whereas if the string is nice, if the string's length is greater than longest nice, right, we can actually just combine this, and the string is also nice, right, then we're kind of going to want to say longest nice is going to be equal to this new string. Last one was 415 milliseconds. This one's like 260 milliseconds, which is pretty good. Kind of cut it in half here. Right, it's about 200. So how could we make this faster? I think one thing we could do, we're checking all strings right now. Or yeah, we're pretty much iterating through all strings. What I think we'd like to do instead would actually be to only check when there are pairless characters, right? So we could do something, right, where we do a pre-check, right, or build our pairless characters, right? Pairless characters array. Right, it's going to be an array of indices, and we're going to want to iterate basically from all these indices, right? Or we could do pairless characters set. Let's do the pairless characters set. Though we don't have to check, right? Because if we look at our string, we have capital Y, A, and then Z. The reality is we don't have to check every not every, but pretty much build every version of YA. It's a little unnecessary, right? We only need to start at YA, right? And also this as well, and at this index. So I think what we could do to further, right, if we do a linear time iteration through and just grab all the pairless characters, we could just say, hey, if this, not if the character equals Z, because we're going to want to know on an index basis, right, what if a character is pairless. So then we'd have Z, right? Then we could have Z, right? And if we have, we'll say if, right, if I is in the pairless set, then we'll skip it, right? Then we're going to want to do our whole thing for that character. Right, so basically we want to use pairless characters to basically optimize this. Here we could say, right, if J, right, if pairless dot has J, right, then we'd like to basically not continue, we'd like to break out of this loop. There's no point checking any further, right, because we need to reach our pairless character. We can also do if pairless has J, or if pairless dot has I, then we want to break just in case, right, when we're going through this array, when we're iterating through the string, we're eventually going to hit Z, right, as we iterate through the top half of the string. We're going to want to skip Z, right, so that's what this if loop is going to help us with. So then we just need to create pairless. Pairless would be a new set of numbers, right, and to do that we'd say for how do we know if a character is pairless? Ultimately, right, we could just load it all into a map. If we use the set, we could use a set, but basically we only know with a map. Actually, no. If we go through and we'll say, if we add a character, right, we'll say Y. You can't do this in less than 2n, right? Because you get to Y, right? We need to check if, lowercase y exists, we only know if we've already loaded it into the set. So we basically need like another temporary set, which is a little bit silly. Say const char of s, and we'll do temp.add char, right? Then you do the same iteration again. This time, right, you only want to add for const char of s if temp.has s.to lowercase, right, and temp.has s.to uppercase, right, then you know that you can add this character to the Pairless, right? But even then, it's not the character we'd like to know, it's the index. So you can do for let I equals 0, I is less than s dot length, I plus plus. Const char is going to be equal to s sub I. We'll change s to char, Pairless.add char. And we don't want to add the character, we want to add the index, right? And I think this should be a little bit faster. 24. Right, and this is actually going to be a set of strings, and then Pairless will actually be in numbers. So let's, I think, wonder if we're having some strange right, so our set, our Pairless has everything in it for some reason, right? If temp.has char.to lowercase and temp.has char.to uppercase, then we want to add it. Right, and if it's Pairless, right, basically right, we only want to add it if it's Pairless, so what we could do is just, it would be easier if we just said if they both exist, we'll continue, right, and then we can have an else if, right, if temp.has char.to lowercase, right, or temp.has char.to uppercase, then we can do Pairless.add I, and then this should fix our weird set, right? There should only be 2 in it. This is actually already slower than the previous version, but maybe it'll be faster on average. This is 160, so that's actually a little bit faster. Or maybe it's just the LeetCode variability. No, I think we ran the other one twice. We got 200, 201. Yeah, this one, it seems to be relatively faster. I mean, I couldn't tell us the time complexity. Maybe there's a way to take it even further, but 162 ms is better than 70%. And we haven't been able to do better than that. Could we take this further? I wish there was a way we could check if a character was Pairless. If a character was Pairless without doing 2 linear time iterations over the string. It's a little crazy. I think you could, right? Because you don't have to iterate over the whole string. You'd only be iterating over unique characters, right? So maybe we could do, or instead of this, oh, we need the index. We need the index of the Pairless character. Yeah, you need the index. Maybe there's also a way, right? Is nice. I think if there's got to be a better way to do is nice, right? The first thing is just going through and creating a set. Is there a way you can check if a string is nice in linear time without right? Without having to iterate through it twice, and also use space. If we take a and we do some bit manipulation, right? Lowercase a is equal to 65. Capital A is equal to 65 plus 26, right? That would be 91. Yeah, that would be 91. So if that's the case, I think you could do a linear time check, but it would require sorting the string first, right? And 2n is probably better than n log n. Right, but say you can do bit manipulation. So I wonder if you ANDed all of this. Right, maybe it would give us a special value. I don't think so though. We could probably optimize this part out if we just kept one set. Actually, no, we couldn't do that. We'd have to do a map. Actually, no, we couldn't do that either. We could not do that either. I think we might have been... Maybe there's a space we can do. If we did sliding window, right? Because right now we're basically doing an n squared operation. If you could do sliding window, or if we did sliding window, we'd say, is this string nice? Is this string nice? No, it's not. Also, we have a pairless character, so you want to skip that. String nice, yes. Is the string nice? Yes. Is the string nice? This is really, really convoluted, but I think you actually could optimize this. We could have an array. Okay, we could have a map of sets. And if we've seen a string before, we could reuse that set. This would also only help if we had a lot of duplicate strings, though. I wonder if I remove this console.log Pairless if it's faster. It's just LeetCode randomness. Now it says 100 milliseconds. You take the average, it seems like it's around, seems like the average is around 140. String divide and conquer. Very interesting. I think there's 4. I think we could remove this 4, this extra 4 somehow. So basically what this does is just create we just print this out, we'd see all of what it creates. It's just Y, YA, and then AAA, and then wait a second. We could do something else. We're also revisiting a lot of strings. We could also have a, this is getting so convoluted. So a visited set where we simply just don't revisit strings we've already seen. Right? All right, if we've already seen a string, then we'd like to continue. So we'll say if visited.has string, then we'll continue. Which means we should print a lot less strings. I forgot to add. Right, we'll do visited.add string. And we have lines here 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or maybe we still want to visit it. We don't want to run is nice. Right. So if string.length is greater than longest.length and right visited does not have string, right, then we want to run is nice. Otherwise, we don't want to run is nice. It's a little faster. Maybe a better benchmark would actually be what strings are running is nice on. Then we can remove this line and we'll see they're only running it twice. Why are we only running it twice? Interesting. So we add visited dot. Visited doesn't have it. Actually doesn't help us that much. Actually, it's just a bit slower since we have to check. Well, maybe for a larger sample size, it's faster. No, yeah. I think that's the point. This is just marginal improvement here. Actually, no point having this. could remove this for loop. If we could just remove this for loop and go into right, so now we have, let's say we remove it, right? Let's say, right, we'll have a string out here. Right, and how will we know we want to restart? What if we say if Pairless has I, right, then we want to restart. Pairless has I, then we want to restart. So we'll say string is equal empty string, right, to be equal to Z, right? And we go to the next iteration, we'll start with lowercase a again. Spacing is all over the place on this. I want to remove J because it no longer exists. Right, so we standard out CC. The longest substring is actually the whole thing. I'm wondering why that is, because if we check Pairless, it should be empty. Oh, wait. Right, so it is empty. We do CC, right, we add the string to it. If string.length is greater than longest nice.length and is nice, then I'm going to say longest nice equals string. Right, doesn't, so we add capital C. Right, but okay, I think I'm seeing what's happening. We don't have to do this version anymore. We just want to know if the string is nice. It still happens because it's up here. That's the problem, right? We still want to visit the whole string. Right, so we want to say is nice string, and then longest nice equals string. That's actually not the case. We want to say longest nice is equal to the string if, right, if string.length is greater than longest nice.length, then it's equal to string. Otherwise, it's equal to longest nice. That should help us with this case where we want to return the earliest string. All right, so our unpaired character is only K, right? So our longest one is actually WYY. So this one's actually strange. Like, let's say we print this one, we should be getting I see. Right, we end up including H the whole time, which we don't want to. And this is where it gets messy as always. I think we can actually fix this. If we actually do what we did earlier, right, instead we said we'd do a map of character to index, right, we can remove the values at these indexes in the map, right, and then we'll know that H has no future partner, so we're going to restart at capital B. Right, and it's actually a problem that Pairless starts as set because we're actually going to want it to be a map of string to number array and then what we'll do is we'll say, right, if we're going through the string, right, then we're going to want to push the value into the array. Right, so actually just say cars or map, right, and we'll say r is equal to if the map has an array for this character. If it does, then get that array. Otherwise, return an empty one. We'll do r.push I, and we'll do map.set car equal to r. We're going to want to print the map. Right, we'll change Pairless to map. And this should still give us an error, but we just want to see that the map makes sense. Right, so I think we're okay here, right? When we check if something is pairless, right, what we just want to do is make sure that at least an array of at least length 1 exists, right? So to check if something's pairless, right, we'll do something like this. If map.has s sub I we want to check if something's pairless. To do that, we're going to need to know if both of its uppercase and lowercase values in the map have a length greater than or equal to 1. So to do that, we can actually do it like this. We'll say car is equal to s sub I. Right, and we'll know something's pairless, right? If we get, we'll just call this lower r, we'll call it map.get car.to lowercase, and then we'll have upper r do to uppercase, and then this is how we'll know something's pairless. We'll say if lower r dot length equals 0 or upper r dot length equals 0, right, then we have a pairless character. This character is pairless. If this character is pairless, we'd like to restart, but also we'd like to iterate through every character for const c of s dot slice starting at I minus string dot length going to I basically. Right, then we're gonna want to do map dot get car, right? It's going to give us an array, and we're going to do dot pop. And then afterwards, we'll set the string equals an empty string. We want to change this car to C. Right, and then we'll change both of these to safe navigation. Another one we could do is we could say if not lower R or if not upper R, right? And then we can go even further and start checking closer. So we do get the right answer for this. Dang. I'm pretty sure X is a pairless character in this string because there's no capital X. There is a capital X. XLE W, and then we just restart, I guess, because yeah, why is W? Why are we starting at W? Restarting at HZCW. S is an unpaired character, actually. Right, so as soon as we get to this W, we restart. Yeah, we're gonna have to peep the solution. Divide and conquer. N squared. Maybe linear time isn't possible. This is 26 times Scala recursive. N squared. Python. So he iterates through the range. And then he says I.swap case not in store. If it's not in the store, so if it's not in the set, then we're going to say left is equal to self the longest. Nice. Oh, so this is recursive. This is divide and conquer. Right, this guy had the same is nice function, right? And if it's nice and it's greater, right? This is kind of what we did. Uppercase, oof. Sliding window, 26, I don't know. Okay, what is going on here? Start, length ands. Oh my God, this is a beefy one. Linear time, this man is a beast. Complete. Yeah, we're gonna have to lock in tomorrow and read this because my brain is fried. So I think tomorrow we'll read this, we'll try and make sense of this solution. And then I think we'll start reading the ADM, and then we'll keep going through our explore card. So